In this chapter 16, we are going to discuss precipitation reaction and another type of equilibrium that associate with aqueous ionic reactions. And here are the overall chapter section that we are going to discuss. We're going to start with 16.1 precipitation reaction. We're going to look at what are the type of precipitation reaction, how can we predict the precipitation reaction product, and how can we write the balanced chemical equation that represent precipitation reaction. And 16.2, we are going to take a look at solubility equilibria, and we will look at the equilibrium constant that associate with the insoluble salt or insoluble ionic compound. And 16.3, we are going to look at multiple equilibrium reaction that involve with each other. We call this couple equilibria. First, let's start with 16.1 precipitation reaction. Please read the OER textbook for the chapter introduction and also 16.1 section. Precipitation reactions are the reaction that form solid products or precipitate. And many reactions of this type involve the exchange of ions between ionic compounds in aqueous solution and are sometimes referred to as double displacement or double replacement reactions. The solids that form during the precipitation reactions are the ionic compounds that are insoluble. We can determine how much the ionic compound can dissolve in solvent or water by looking at their solubility, which is the extent at which a substance may be dissolved in solvent. And we can define that substances with relatively large solubility are soluble, and substances with relatively low solubility are insoluble. And a substance will precipitate when solution conditions are such that its concentration exceeds its solubility. Ionic compound that dissolves in water and give clear, transparent, homogeneous mixture is considered to be soluble, such as when sodium chloride dissolves in water, it will give clear, transparent, homogeneous solution. And same for potassium nitrate as well. And for those ionic compound that dissolves in water less than 0.01 molar and give suspension or milky mixture, they consider to be insoluble. For example of this is calcium carbonate or chalk that when we dissolve in water, it can dissolve in a very small amount, and majority of calcium carbonate stay as solid. In reality, solubility is continuous, which means that there are those ionic compounds that do not dissolve in water at all, and it's ranging all the way to those ionic compounds that dissolve in water in a great extent. Scientists have determined solubility for various salts by dissolving them in water and see which one is soluble and which one is not soluble. They have discovered the pattern of the solubility. These patterns are called solubility rules for ionic compound in water, as summarized in this table. This table categorized in two categories. One is soluble ionic compound and the other is insoluble ionic compound. Ionic compounds that contain these ions are generally soluble ionic compound. However, there are exceptions. And the ionic compounds that contain these ions generally are insoluble, but there are exceptions. For the hydroxide ions exception, I would like you to add calcium ions and strontium ions, as well as ammonium ions to be part of the exception for the hydroxide ion. Another thing that I would like to point out from this table is the acetate ion. Please note that this is one of the forms of how to write acetate ion. Another way to write acetate ion would be CH3COO- or CH3CO2-. Of these three forms represent the same acetate ions. Let's take a look at example 1. Determine if each compound is soluble or insoluble when dissolved in water. These compounds are ionic compounds because they contain metals and nonmetals. So in order to determine their solubility, we are going to use the solubility rules for ionic compound. First, let's take a look at copper sulfide. Copper is not on the list. However, the sulfide is on the list. Here's the sulfide. If you look at the sulfide is part of the insoluble ionic compound. But let's take a look at exception. Exception would be when the sulfide combine with group 1 or ammonium ions. Copper is not part of the exceptions, therefore copper sulfide would be insoluble ionic compound, which means it will not dissolve in water. Next, magnesium phosphate. Phosphate is on the list of insoluble ionic compound, and magnesium is not part of the exception, therefore again magnesium phosphate would also be insoluble ionic compound. Next, lithium carbonate. It doesn't matter whether you are looking at lithium or carbonate because both of them are listed on the table. Lithium ionic compound that contain lithium ions are soluble, and there is no exception. If you do the analysis by using carbonate ion, it will give you the same result as well because the ionic compound that contain carbonate ion is insoluble, but the exception is that when the carbonate ion combine with group 1 metal cation and lithium ion is the group 1 metal cation, therefore lithium carbonate would be soluble ionic compound. Next, ammonium chloride. Both ammonium and chloride are listed on the table also. You can use one or the other. Ammonium ions is a soluble ion with no exception, therefore this ionic compound would be soluble ionic compound. Next, we are going to use this concept to help us determine the precipitation reaction. Keep in mind that the precipitation reactions are the reaction that produce insoluble ionic compound. Therefore, if the product that we determine are insoluble salt, we can classify that type of reaction to be precipitation reaction. And here are the general approach of how to write precipitation reaction. I'm going to use this general approach to help me write the precipitation reaction for next example. Example 2. Write a balanced chemical equation for a precipitation reaction when the following solutions are mixed. If no reaction occurs, write no reaction on the product side. Let's take a look at number 1, copper 2 sulfate and sodium hydroxide mixed together. First step, we will need to determine the chemical formula of the two reactants. For copper 2 sulfate, the chemical symbol for copper is Cu. The Roman numeral 2 tells us the charge of the transition metal, which is copper. Copper is a metal. Metal is most likely to lose electron, therefore the charge of the copper would be 2+. Sulfate is a polyatomic anion that has the chemical formula of SO4 2-. As you see, when copper 2+ and sulfate 2- combine with each other, they require 1:1. Therefore, the chemical formula of copper 2 sulfate would be CuSO4. Copper sulfate is a soluble ionic compound, therefore the physical state of this would be aqueous. Do the same thing for sodium hydroxide. Sodium is Na+ and hydroxide is a polyatomic ion OH-. Therefore the chemical formula of sodium hydroxide would be NaOH. And sodium hydroxide is a soluble ionic compound, therefore the physical state of this would be aqueous. And because we are going to react copper sulfate with sodium hydroxide, so we need to add a plus sign for it. In order to determine the product, next we need to exchange the cation and the anion between the two reactants. The copper cation will combine with the hydroxide anion, and the sodium cation will then combine with the sulfate anion. And because we know the charge of copper and hydroxide ions, we know that copper is 2+, but hydroxide ion is 1-. To make this compound to be neutral, you will need 2 hydroxide ions per 1 copper. And same thing for sodium sulfate as well. For a neutral compound, we will need 2 sodium ions for 1 sulfate ion. Note that when you write the ionic compound chemical formula, you need to write metal first, followed by non-metals. Again, metal first, followed by non-metal, or cation followed by anion. And note that when you have the polyatomic ions, you will need to use parentheses before you do the subscript. However, for the ions that are not polyatomic ions, you can just write the subscript right away without the parentheses. Next, use the solubility rules for any compound in water to determine the physical state of the product. For copper hydroxide, Hydroxide are generally insoluble ionic compound, and copper is not one of the exceptions. Therefore, in this case, copper hydroxide is insoluble. So the physical state of the insoluble ionic compound would be solid. Next, for sodium sulfate, sodium generally is soluble ionic compound, and there is no exception. Therefore, sodium sulfate would be soluble. For soluble ionic compound, we are going to use physical state of aqueous because it's dissolved in water and form aqueous solution. And the insoluble ionic compound, which is the solid, this is what we call precipitate. This means that when you mix copper sulfate together with sodium hydroxide, you are going to observe copper hydroxide form as a solid during the reaction. And this is an example of precipitation reaction. Last step of writing out the chemical equation is to balance the chemical equation. As you see on the right side, we have 2 hydroxide and 2 sodium. But on the left side, we have only 1 sodium and 1 hydroxide. Therefore, we will need to add 2 as a coefficient in front of sodium hydroxide. Now, this chemical equation is balanced. Next, I would like you to pause the video and complete the next example. Resume the video again when you finish. Potassium is in group 1, has a positive 1 charge. Nitrate is polyatomic anion NO3-. Sodium is in group 1 with positive 1 charge. Chloride is in group 17 with negative 1 charge. So the chemical formula of the 2 reactants are KNO3 and NaCl. These 2 ionic compounds are soluble ionic compounds according to the solubility rules. Potassium and sodium are in group middle 1 with no exception that are soluble ionic compound. So the physical state of both potassium nitrate and sodium chloride would be aqueous. Next step is to exchange the cation and anion between the 2 reactants. Potassium will combine with chloride and sodium will combine with the nitrate. So the product would be potassium chloride and sodium nitrate. Next, determine the solubility of the 2 products. Potassium chloride, potassium ion is generally soluble with no exception. Therefore, potassium chloride would be soluble ionic compound. Same for sodium nitrate as well. Sodium ions is generally soluble ionic compound with no exception. Therefore, the physical state of both potassium chloride and sodium nitrate would be aqueous. Note that the mixture between potassium nitrate and sodium chloride doesn't produce any precipitate or any solid ionic compound. Therefore, this reaction is not a precipitation reaction, and we can say that there is no reaction between potassium nitrate and sodium chloride. Or we can rewrite this reaction as no reaction on the product side. Precipitation reaction can be used in many applications, including water treatment. For example, the treatment of hard water. Hard water contains calcium ion and magnesium ion. These 2 ions can form precipitate that can clog the pipe, leave the stain on the glass, or even change the clothes color when you wash it with hard water. One of the various ways to treat the hard water is to use sodium carbonate or soda ash, commonly known as water softener, to treat hard water. Sodium carbonate, when it dissolves in water, it will dissociate into sodium ion and carbonate ion. These carbonate ion then can combine with calcium ion in hard water or magnesium ion in hard water to form solid. Then you can filter out the precipitate to get rid of the calcium ion and magnesium ion. Then the water is no longer hard water. Please practice more of this concept by doing the DIY problems on page 61. The answer key for this will be posted on Moodle. The chemical equations written in the previous example do not always demonstrate what is happening during the chemical reaction. So to get a clearer picture of what is taking place during an aqueous reaction, we are going to represent the chemical equation by the complete ionic equation and net ionic equation. You learned these 2 types of equations before when we talk about acid-base neutralization reaction. We are going to apply the same idea here. For those that are strong electrolyte, they are going to be dissociated completely, and those are non-electrolyte, they are going to stay as a compound or molecule. And for the insoluble ionic compound that do not dissolve in water will stay as molecule because they will not dissociate. Let's take a look at example 3. Write the balanced molecular, complete ionic, and net ionic equations for the reaction between lead 2 nitrate and potassium iodide. Again, the chemical symbol for lead is Pb. The Roman numeral 2 represents the charge of the lead, which is 2 plus, and nitrate is polyatomic ion, NO3 minus. Potassium is K. In group 1 would be K plus, and iodide in group 17 would be I1 minus. For a neutral lead nitrate compound, we see that for every 1 lead ion, we'll need 2 nitrate ions. And for potassium iodide, for every 1 potassium ion, we will need 1 iodide ion. Next, exchange cation and anion of the two reactants to get the product. For lead iodide, you see that every 1 lead ion would require 2 iodide ions to make it to be neutral molecule. And for potassium and nitrate, it would be 1-to-1 ratio. Next, balance this chemical equation. For every 1 lead nitrate, it will require 2 mole of potassium iodide to produce 1 mole of lead iodide and 2 mole of potassium nitrate. Last step is to determine their physical state by looking at the solubility rules for each of these compounds. Lead nitrate contains nitrate ion that is going to be soluble ionic compound with no exception. For potassium iodide, it contains both iodide and potassium that is also soluble ionic compound. For lead iodide, it contains iodide with the exception of that if the iodide paired up with lead, the result would be the insoluble ionic compound. For potassium nitrate, both potassium ions and nitrate ions is the soluble ionic compound with no exception. For the soluble ionic compound, the physical state would be aqueous, and for the insoluble ionic compound, the physical state would be solid. Because mixing lead nitrate and potassium iodide form solid insoluble ionic compound, therefore, this reaction is an example of precipitation reaction. This chemical equation is called molecular equation because every species stays as molecules. However, ionic compounds, when they dissolve in water, they will dissociate to form ion-dipole interaction between ions and water molecules. Therefore, these compounds will not stay as molecule, but they are going to dissociate into their cation and anions. The species that we are going to dissociate for the complete ionic equation would include the strong electrolyte, such as soluble ionic compound, strong acid, and strong base. Everything else will stay as molecule, including insoluble ionic compound. If you look at the molecular equation, species that we are going to dissociate would be lead nitrate, potassium iodide, and potassium nitrate. The species that would stay as molecule that do not dissociate would be lead iodide. To dissociate lead nitrate, the result would be lead 2 plus ion. Physical state still stay the same as aqueous, plus lead nitrate contains 2 nitrate. Therefore, when it dissociates, the 2 become coefficient with the nitrate ion in the aqueous solution. And for potassium iodide, because we have 2 molecules of potassium iodide, therefore when it dissociates, it's going to give off 2 mole of potassium ion and 2 mole of iodide ion. And because lead iodide is insoluble salt or insoluble ionic compound, therefore it will stay as molecule, it will not dissociate. It's indicated it doesn't dissolve in water, so it's going to stay as solid molecule. And the next molecule is potassium nitrate. There are 2 molecules of potassium nitrate, therefore when it dissociates, it's going to give off 2 potassium ions and 2 nitrate ion. Note that the physical state still stay the same as from the previous type of molecular equation. If you look at this complete ionic equation, you can notice that this equation contains potassium on both sides of the equation and also nitrate ion on both sides of the equation as well. Therefore, both potassium ions and nitrate ions would consider to be spectator ions, which means that they do not participate in the reaction, they just float around. They are there to help balance the charge of the ions. The net ionic equation represents what actually participate in the reaction, and the species that participate in the reaction would be everything except the spectator ions. Therefore, in this case, it would be lead ions plus 2 iodide ions to form lead iodide. Note that if the net ionic equation is not in the smallest ratio, you will need to reduce the coefficient to be the smallest ratio. For example, 2A plus 2B become 2AB, you will need to reduce this to be A plus B to become AB. You will need to show it in the smallest ratio. Please practice more of this concept by doing the DIY problem on page 63. The answer for this will be posted on Moodle. Next, precipitation stoichiometry. Precipitation stoichiometry uses the same idea as the acid-base stoichiometry that we learned in the previous chapter. We are going to use the stoichiometric factor to help us derive the conversion between mole to mole and help us to find out the grams of the precipitate, or to find out the volume or concentration of the solution that need for the reaction. Here are the examples. Example 4 is an example of using volume of A and molarity of A to convert to mole of A, and then use the mole to mole ratio to convert to mole of another species B, and eventually use the molar mass to convert to grams. Example 5 is an example of conversion from grams of A to mole of A, using mole ratio to convert to mole of B, and use the volume of B given to eventually derive to molarity of B. Example 6 would be an example of conversion from grams of A to mole of A, use the mole ratio to go to mole of B, and use molarity of B to obtain the volume of B. Note that the important part of all of these examples is the mole ratio that allows you to convert from mole of something to mole of something else. Therefore, in this case, you will need to write a balanced chemical equation so that we can use the stoichiometric factor to help us to convert between mole of A to mole of B. So I'm going to go ahead start with write out the chemical equation for the reaction from example 4. Vanadium 4 nitrate react with potassium carbonate. Vanadium chemical symbol is V, and Roman numeral 4 represent the charge of vanadium 4+. Nitrate is NO3-, potassium is K+, and carbonate is CO3 2-. Therefore, the chemical formula of vanadium would be every 1 vanadium would require 4 nitrate. And because vanadium nitrate contains nitrate that is soluble, therefore this ionic compound would be soluble, so the physical state would be aqueous. And for potassium carbonate, for every 1 carbonate is required 2 potassium, and this ionic compound contain potassium ions with no exception. Therefore, this ionic compound would be soluble, so the physical state would be aqueous. Next, do the exchange of the ions between the two reactants. Vanadium will combine with carbonate and potassium will combine with nitrate. And as you see the charge of vanadium and carbonate, we can see that the charge of carbonate is 2-, vanadium is 4+. Therefore, for every 1 vanadium is required 2 carbonate to make it neutral, and for potassium and nitrate would be 1-to-1. In order to determine the physical state of these two compounds, again, you will need to use the solubility rules. According to the solubility rules, the vanadium carbonate would be insoluble and potassium nitrate would be soluble. Therefore, the physical state of vanadium carbonate would be solid and potassium nitrate would be aqueous. The last step is to balance the chemical equation. Example 4, the problem asks for how much of the precipitate. In this case, the precipitate that we determine would be the vanadium carbonate can be produced when 75 ml of 0.345 molar of vanadium 4 nitrate is completely react. So if you're looking at between these two, you see that the ratio between these two would be just 1-to-1 mole ratio. Therefore, in this case, you are going to need to convert the volume and molarity of vanadium nitrate into mole first, and then use the mole ratio between these two species to convert to mole of the precipitate. Then use molar mass of the precipitate to calculate for grams of the precipitate. And you will get the grams of the precipitate equal to 4.42 grams of vanadium carbonate. Please pause the video to complete example 5 and 6. Once you finish example 5 and 6, please resume the video again to check your answers. Here is the balanced chemical equation for example 5. Note that the precipitate that formed is iron 3 fluoride. Example 5 giving the information of the mass of the precipitate, which is the iron 3 fluoride, and ask for the molarity of rubidium fluoride, which is this reactant right here. Therefore, what we need to do is first convert grams of iron fluoride into mole of iron fluoride by using its molar mass. Then convert the mole of iron fluoride into the mole of rubidium fluoride by using the stoichiometric ratio. You will get the mole of rubidium fluoride equal to 0.145 mole. Next, to find out molarity of rubidium fluoride, we are going to need to divide mole of rubidium fluoride by its volume, which is 50 milliliter convert to liter, which is equal to 0.05 liter. And we will get the molarity of rubidium fluoride equal to 2.91 molar. For example 6, do the same thing similar to example 4 and 5 by starting with writing a balanced chemical equation. You will see that the precipitate that form in this reaction would be calcium carbonate. This problem gives the grams of the precipitate, which is calcium carbonate, and ask to calculate the volume of ammonium carbonate. The first step is to start with the grams of the precipitate and convert these to mole by using the molar mass of calcium carbonate. Then use the mole ratio between calcium carbonate to convert to mole of ammonium carbonate by using the stoichiometric ratio. Next, use the molarity of ammonium carbonate to convert from mole of ammonium carbonate into the liter of ammonium carbonate, and then convert that into milliliter. You will get the volume of ammonium carbonate that is required to react with calcium chloride equal to 36.4 milliliter. To master in this type of calculation, you will need to practice the DIY problem on page 65. Again, the solution for this will be posted on Moodle.